In this video, we are going to graph a logarithmic function by hand without using our graphing calculators or using Desmos. So log functions can be graphed just like all of the other functions we have studied so far this semester by first identifying the parent function and then using our knowledge of transformations. This function is f of x is equal to log base 2 of x plus 4. So this plus 4 is going to end up causing a transformation. So if we ignore that plus 4 right now, what we have left here is essentially our parent function. So our parent function will be y is equal to log base 2 of x. Now, to graph a logarithmic function quickly without our calculator, it's helpful to take that logarithmic equation and rewrite it in its equivalent exponential form. And remember, to do that, we're going to always start with our base. In this case, our base is 2. And we're going to loop around the equal sign. So 2 raised to the y power will be equal to x. So in exponential form, that's 2 to the y power is equal to x. And remember why this is. This is essentially because a logarithm is an exponent. So in this case, when we see that we have log base 2 of x is equal to y, that tells us that y is going to be our exponent. Essentially, 2 to what power is going to give us x. So we can graph 2 to the y equals x by making a quick table. Now we want to be smart about making our table. Normally we fill up the x side of the table with values, but if we look at 2 to the y equals x, it would be much easier to substitute in y values and then figure out what the x values are. So we're going to actually fill up the y side of our table from -2 to 2 is a good place to start. And then these are going to be our exponents. So for example, if we have -2 for y, then we're going to find 2 to the -2 power. That negative exponent makes this 1 over 2 squared. Therefore, the x value would be 1/4. So plotting that point, we're going to go right 1/4 and down 2, and you can just estimate the 1/4. 2 to the -1st power would be 1 over 2 to the 1st power, which is going to be 1/2. So right 1/2, down 1. We've got 2 to the 0 power, which we know is 1. So that's here. 2 to the 0 power is 1. So we have 1, 0. 2 to the 1st is 2. 2 to the 2nd is 4. And then we actually do have room to go ahead and go to a y value of 3 because 2 to the 3rd power would be 8. So we can plot 8, 3. And then hopefully this triggers your memory of the basic shape of a log graph. And you have to be careful because if you were to use a graphing calculator, for example, sometimes the graphing calculators show that the graph actually stops. But we have to understand that this graph actually will continue on. And there's actually a vertical asymptote here. So this graph is going to continue on and hug the y-axis. And again, think about y. If I were to choose a y value, I could even choose a y value like a -10, for example. Then I would have 2 to the -10th power, which is 1 over 2 to the 10th power, which is an itty bitty tiny number, extremely close to 0. So if you could imagine, that would be down here if we were going right just a little bit and way down here at -10, you can see that the graph does continue on. So be careful using your graphing calculator. The graph doesn't end. It does continue on down forever. It has a vertical asymptote. And in fact, I recommend that you go ahead and graph in that asymptote. I always use a different color. So this imaginary line that this graph is going to get very, very close to, and this is a vertical asymptote, so the vertical asymptote for the parent function will be x equals 0. Let's pause here and just go back over a few reminders. When we have our basic parent functions for logarithms, there are 4 common features. We always expect to have an x-intercept here of 1, 0. We always expect to have a vertical asymptote of x equals 0. And then remember, the domain for the parent function is always going to be 0 to infinity, because we cannot take the log of a negative number and we can't take the log of 0. And the range, lowest to highest, will be negative infinity to positive infinity. Remember, this domain and range is for the parent function, y equals log base 2 of x. It's also worth noting that because the base of our logarithm was a 2, and that value is greater than 1, then we expected this parent function to be increasing. And you can see if I trace from left to right, indeed my y values are getting larger. So now let's work on our transformation. So looking back at our original function, f of x is equal to log base 2 of x plus 4, we see we have this plus 4 in the parentheses with the x, so it's impacting the x values. And so this is going to be a shift to the left 4. So we're basically going to take our entire graph and shift left 4. And I recommend that you always move the asymptote first. So our asymptote was at x equals 0, but if we shift left 4, then we have a new asymptote at x equals negative 4. So our function f of x, the VA, or vertical asymptote, will be x is equal to negative 4. And by graphing the asymptote first, then you're not going to need to worry about any of those little fractional ordered pairs. You can just plot the ordered pairs that had nice whole numbers. So for example, the x-intercept here that was at 1, 0, we're just going to shift that point left 4. So that's going to move over here and become negative 3, 0. And then we had another point at 2, 1. Shift that point left 4 as well. So go ahead and do that for the 4, what I call good points that we have on the graph, just meaning that their x and y values were nice whole numbers. You don't need to worry about the fractions because, again, we're recognizing that this graph is going to look very much like its parent function. Therefore, it's going to have the same basic shape. And because the parent function had a vertical asymptote, this graph is going to as well. And this is our final graph, f of x. Now, we can figure out the domain by looking at this graph. Remember domain, we're looking at the x values. So we're going from the left side of the graph to the right side of the graph, leftmost to rightmost. And you know, because we have that vertical asymptote, this graph never has any x values smaller than negative 4. So our domain is going to be all the x values from negative 4 to infinity. You can write x as an element, if you want to, of the interval from negative 4 to infinity. And I'm using a parenthesis on negative 4 because this function is never going to intersect its vertical asymptote. And then our range, remember, are the y values, lowest to highest, or bottom to top. And this graph does go down forever, and it also does go up forever. And even though the right-hand side of the graph over here, it might look to you like it's leveling off, it is not. It's still growing, it's just growing at a very slow rate. So the range would be all of the y values from negative infinity to positive infinity. So we can write y as an element of the interval from negative infinity to positive infinity. Just a side note, remember that this fancy math notation here, the x is an element or y is an element, it's not required, but I always like to show it to you so that you're prepared if you do see it in the future. Last thing before we finish, I always like you to check that domain algebraically because we just figured out the domain by looking at our graph. And if we had made a mistake with our transformation, let's say we had moved in the wrong direction, we could catch that mistake if we were smart about figuring out our domain algebraically. So looking back at the original function, not looking at the graph, but at the original function, remember that the argument is what you're taking the log of, which in this case is the quantity x plus 4. And for a logarithm, those arguments must be positive. In other words, x plus 4 must be greater than 0. You cannot take the log of a negative, and you can't take the log of 0. So if x plus 4 must be greater than 0, and we solve this inequality by subtracting 4, then we know that x must be greater than negative 4. So that supports that our domain should be from negative 4 to infinity, which is indeed what we got earlier, and that also then verifies that our graph is correct.